Hello everyone. We are now going to begin our lecture on a very important topic on statistics, which also forms the basis of several inferential studies. It's called the normal distribution. We will start with understanding what a density curve is, and then from the density curve, we will talk about the standard normal curve and the standard normal distribution. And then we will talk about areas under the curve. Now, areas under the curve tell us what proportion of observations lie above a certain value or below a certain value or between two values. So we will try to understand and learn how to find those areas. So we will go into more details in the subsequent slides. We will start with an understanding of a density curve. A density curve essentially portrays the distribution of observations. Previously, we had learned to portray the distribution of observations graphically by what's called a histogram. So, histogram was a form of graph which told us which observation occurs with more frequency or with more proportion, proportionately which observation occurs more than the other observations, right? Now, a histogram was a set of vertical bars over a horizontal line, right? And their heights represented the frequency or the proportion of occurrence of a particular observation, right? Now, when we superimpose a curve over the histogram, it's what it's called a density curve. And just like the histogram covered all observations, the density curve also covers 100% of the observations. So let's read the basic properties of density curves. Property 1 says a density curve is always on or above the horizontal line, just like the histogram. And property 2 says the total area under a density curve and above the horizontal axis equals 1. So if we are talking in terms of relative frequency, then the total area will be 1. If we are talking about probability, even then the total area will be 1 because the sum of all the probability values will equal 1, and so will the relative frequencies, correct? However, if we are talking in terms of percentages, then the curve, a density curve, will cover 100% of the observations. Now, density curves often help us determine what percentage of values are less than a certain observation, or what percentage of values are greater than a certain observation, or what percentage of values could be between two observations. And that percentage equates to what's called the area under the curve. If we are talking about what percentage of values or what proportion of values are less than a certain value, then it's the area to the left of that observation. If we want to know what percentage of values are above a certain observation, then you have to look at the area to the right of that particular observation. And likewise, if we want to know what percentage or what proportion of values are in between two observations, we have to know how to find the area between the two observations. So that's what we we are going to learn in this lecture. We will learn how to find the areas to the left or right or in between two observations. Okay, so let's read what is on the slide here. It says for a variable with a density curve, the percentage of all possible observations of the variable that lie within any specified range equals, at least approximately, the corresponding area under the density curve expressed as a percentage. So that's what I said, that if you are interested in knowing what percentage of observations lie above, below, or in between observations, then we have to consider the area under the curve, different sections of areas under the curves, depending on what we want to find. Now, variables often have their own type of distribution. They could be right skewed distribution or they could have a left skewed distribution, but variables that have a distribution that follow the shape of a normal curve is said to have a normal distribution or is called a normally distributed variable. Okay, now there are a lot of variables in real life which have been found uh, after a lot of study to have a certain distribution, and that's how people come to the conclusion, or statisticians come to the conclusion that this variable is normally distributed or not. For example, IQs are considered to be normally distributed variables. All right. Similarly, we will see in the next slide heights. All right, people's heights are often normally distributed. So we will use that as an example to study further this whole normal distribution topic. Here is an example of a normally distributed variable. We have been given a frequency table here with heights of about 3,264 individuals, and the data is arranged in cut point grouping interval form. Remember, cut point grouping is used for continuous numerical data, continuous quantitative data, and heights represent continuous quantitative data, right? Continuous quantitative data is measurable data. Height is something you measure. So they had to create the grouping here as cut point grouping so that it fits decimal values. And then they tallied the data and created a frequency chart. And once the frequency chart was created, they calculated the relative frequencies using the F over N formula. What is N? N is the sum of all the frequencies, correct? Here is what N is, 3,264, or the sum of all the frequency values. And once we got our relative frequency values, shows here a histogram created from the relative frequency. It's a relative frequency histogram, but along the x-axis are all the actual data values for this particular example, heights, starting from 56, which is the lowest value on our table, and the highest value is 74. So that's what has been shown on the x-axis, and along the y-axis it's the relative frequency values. Okay, now as we can see that this curve superimposed on the histogram. Initially, we start with a histogram and then we superimpose a curve on over the histogram, and this curve definitely is a normally distributed. First of all, it's a bell-shaped curve, correct? And it is a very symmetrical curve. That means if we slice this curve from the center, from its peak, it pretty much divides the two sides into two equal parts, into mirror images of each other. Okay, now this is a curve using actual data. Another thing that this curve will help us determine is find the of proportion of values which are above a certain value or lower than a certain value or between two values. Remember, we talked about the density curve gives us information through its area to determine what proportion of data or observations lie on the left side of a value, which means lower than a certain value, or to the right of a certain value, or higher than a certain value, or between two values. So we see here a shaded region, right? This blue area between 67 and 68. So if we were asked what proportion of data, what proportion of observations lie between 67 and 68, we would be we would have to rather find this area between 67 and 68, and that would be equal to the proportion, the relative frequency for heights between 67 and 68. So let's look at our table here. Between 67 and 68, the proportion or relative frequency is 0.0735, and this area, it will also be approximately equal to 0.0735. This is 0.0735. Okay, if they ask you, or if someone asks, what proportion of values are between 64 and 65? That's the histogram or the rectangle right at the center, right? 64.65. This area is going to be equal to, let's see, how much is it? 0.1713. 0.1713. All right. What about if someone asks the proportion of heights? Let me write that here. Proportion, what is the proportion of observations less than 61 inches? 61 inches. What we would have to do is we would have to find 61 on this diagram. It's located right here. Draw a line up vertically to touch the curve, and less than 61 inches. Less than 61 inches would be all this area to the left of 61. That's all values less than 61, correct? So if you find the area of this region under the curve, that would be the proportion of observations that lie below 61. So if we go back to our table, let's see what are the proportions here. 0.0009 plus 0.0018 plus 0.0080 plus 0.0227 plus 0.0450, right? So these four values would need to be added up. These values would need to be added up, and that would be the area of this region, this green shaded region. Okay, similarly, if somebody says what proportion of values are 69 and above, all right, what proportion of observations lie above 69 inches? Again, you have to find your 69 on the horizontal line, pull up or draw a line vertically up to the curve, and then shade the area to the right. So values greater than 69 would be to the right of 69, correct? So if you add up all the areas or all the relative frequency values which is above 16, which are above 69. So starting from 0.199, all these values, if you sum them up, that would be this area. All right, that would be this area. This. So you have to sum up all these relative frequency values, and that would be the area to the right of 69. So we are going to come up with a way of calculating or finding these areas under the curve without having to use a frequency table. All right, we'll be using a different kind of table, but not a frequency table, and we will be spared of many calculations, all the work behind creating a frequency table. And another thing that we are going to learn is, instead of having a curve for every example or every situation, we will learn how to create a standard normal curve which will be applicable to any normally distributed variable, whether it be heights or whether it be IQs. As long as the variable is normally distributed, we can use the standard normal curve for it. Okay. Now this slide summarizes what we just said about the areas under the curve and the relative frequency values or the percentage values of observations. All right, so normally distributed variable and normal curve areas. For a normally distributed variable, the percentage of all possible observations that lie within any specified range equals the corresponding area under its associated normal curve expressed as a percentage. This result holds approximately for a variable that is approximately normally distributed. So what this means is, as long as we have a normal distribution, as long as we have a normal distribution, right, then the area under the curve, which corresponds to a certain value. All right, so the area to the left or right of a curve corresponding to a certain value would represent the percentage of all possible observations, and that's what we discussed in the previous slide with the example of heights. Correct? We said if we want to find the percentage or the proportion of values or proportion of observations that lie between a height of maybe 64 and 65, then we have to find the area between those two values to tell to first of all to find the relative frequency, and once we find the relative frequency, we can convert that relative frequency or the proportion value into a percentage form. So what it says again here is that the the percentage of all possible observations that lie within any specified range. Now this we said was above. So if I have another value under the curve here, another point in this on this horizontal line, if we want to know what percentage of values lie between these 2 points, then we have to find the area of this region, which will be in decimal form because it will be a relative frequency value. But once we have a relative frequency value or the proportion value, we can always convert that to percentage form by multiplying it by 100. Okay. Now, when we looked at the normally distributed variable and its corresponding distribution, the curve for that distribution, if you recall on that example on height, Along the x-axis, we had all the heights laid out before us. For example, 64, then 65, then 66, and all the way to 74. The x-axis was broken down into all the different heights that were in our data set, and then we created a histogram and we superimposed a normal curve over it, which ended up being a normally distributed curve. Now, instead of using actual values for heights or IQs, what we can do is we can use our z values and scale the x-axis based on z values. Because in a normally distributed curve, we always know that the mean is going to be at the center of the curve. The peak is located at the mean, correct? So we know that since the mean is located at the center point, right, we can just use the z values, the corresponding z values. What is a z value? A z value represents the position, correct? The position or the distance of an observation. The distance or position of an observation from the mean. That's what a z-score or a z-value is. And if we know that the mean is located at the center point of a normally distributed curve, then we can represent the mean as with a z-value of 0. And then on the right hand side, we will have our +1, +2, and +3 z values. And on the left hand side, we will have -1, -2, and -3 z values. All right. All this we had studied way back in when we were talking about standard deviation, variations, and all that, when we were doing our descriptive measures of central tendency and so on. So this is a repeat of what we already studied before. Should be a review for you at this point. All right, but we can replace our actual values with z values in a in our normal curve. And once we do that, it's no longer just a normal curve, it becomes a standard normal curve. Why standard normal curve? Because we can use this curve for any normally distributed variable, whether it be heights or whether it be weights or whether it be IQs or whether it be test scores. We can use it for any purpose. All right, then that's why it's called a standard normal curve. Now let's look at some of the properties of a standard normal curve. A standard normal curve is bell-shaped. It's centered at mean mu. All right, so in a standard normal curve, the mean will be located right at the center, and it's close to the horizontal axis outside the range mu minus 3 standard deviations to mu plus 3 standard deviations. What this means is that the curve will get closer and closer and closer to the horizontal axis as it heads towards +3 standard deviation. That means a z-score of +3 or a z-score of -3. Now it's not going to touch the x-axis or cross the line, the horizontal axis, but it'll get as close as possible as it moves towards +3, a z value of +3 and a -3. So you have to remember these rules, and a standard normal curve is always symmetric. So we will be using all these facts when we go on to working the different problems using a standard normal curve and normal distributions. Now this is the same thing that we just spoke about, the standard normal curve. We see here a picture of the standard normal curve. We see along the x-axis, instead of using actual values, actual observations like heights or weights or IQs, we have they have this scaled, the x-axis scaled, with z-score values with 0 at the center, which also represents the position of the mean. And then on the right hand side, we have 1, 2, and 3. And on the left hand side, we have -1, -2, and -3. All right, now, if you recall, and let me remind you about the formula of the z value, it's z equals x minus mu over sigma, correct? This gives us the distance of an observation in unit standard deviation from the mean. So distance of an observation from the mean in units standard deviation. Unit standard deviation means the standard deviation being 1. So a normally distributed variable having mean 0 and standard deviation 1 is said to have the standard normal distribution. Its associated normal curve is called the standard normal curve. And a normally distributed curve is based on two parameters, the mean and the standard deviation. In order to find the z value, you must know the mean, you must know the standard deviation, and based on the value of the mean and the value of the standard deviation, your z value will change. All right, and of course the x represents here the particular observation whose distance you want to find, whose distance from the mean you are trying to find in units standard deviation. Now this is another way of looking at the standard normal curve. This picture on the top, the graphs on the top, is they are based on actual values, and you see their values, the actual values range from -6 to +16, and on this line, on this horizontal line, we see three different curves with three different values of means and three different values of standard deviations. All right, so this green curve, which looks like a standard, which looks like a normal curve, which is a normal curve. And then we see this red curve here that is a tall, narrow curve. It has a narrow rising up narrowly the two ends. And then we have a very spread out curve, all right, a short, but this curve has spread out over a wider area. All right, and if you look at the standard deviation values, the green one has a standard deviation of 1, the red one has a standard deviation half, and the standard deviation of this orange curve is 2. So we see that as the standard deviation values increase, the spread of the curve increase. It becomes a wider curve. As the standard deviation values decrease, the lower the standard deviation value, the taller and narrower is the curve. Right? Now, all these different curves, if you change these actual values to z values like they've done here, they can all be collapsed into one standard curve. So if you calculate all these z values, the mean will always be located at the center because these are all normally distributed curves, normally distributed variables. All right. So for a normal distribution, mean is always located at the center, and then the rest of the data will fall under a symmetrical bell-shaped curve called the standard normal curve. Right, and again, this is the formula to calculate z, which is x minus mu divided by sigma. So this slide essentially tells us or reinforces the fact that all kinds of variables, as long as they are normally distributed, can be collapsed and fitted into the standard normal curve once you change the actual values and represent them as z values. We will now learn how to find percentages between or to the left or to the right of a specific value of a variable using a standard normal curve. Now, in this picture here, the first picture on the left shows a normal curve. This is not a standard normal curve, it's just a normal curve because on the x-axis it has actual values with the mean at the center, and A and B are values of observation, of specific observations from the data set. All right, it's a normal curve. It's not a standard normal curve because on the x-axis we have actual values from our observation with the mean at the center. So in order to find the proportion of values or percentage of values between A and B in a normal curve, all we need to do is find the area under the curve between these two values. However, we cannot just take these individual values to find the area. We first need to convert the A and B values to Z values and represent them on a standard normal curve. So the first step in finding percentages from a curve is to convert your observations to z values and represent them on a standard normal curve. Again, standard normal curves have z values on its horizontal line on the x-axis, whatever you may call it, on the x-axis or the horizontal line, and only then we can find the area because the areas that will be given to us pertain to z values and not to actual observation values. All right, so that's what they have here. Z equals x minus mu over sigma is the formula to find z. So using this formula, we first have to find the z value for A, then the z value of B, and then we will convert our graph, our normal curve, to a standard normal curve, and then these two areas will be actually the same. All right, so once we convert our curve to a standard normal curve, we can look up a table called the z-table and calculate the area between the two values. Right? So in the next step, we will learn about how to go about finding the areas from a table. Before we learn how to read areas from a z-table, we will discuss some properties which will give us some facts about the standard normal curve, and we will need to apply these facts or rules from these properties when calculating the areas and then percentages. All right, so property 1 says the total area under the standard normal curve is 1. So the total area under the curve is 1 because it covers 100% of the observation. So if you are thinking of in terms of percentage, then the percentage of observations under the curve is 100% or very, very close. Remember, between -3 and +3 z values, the empirical rule says we have 99.7% of observations covered. So that, which is very close to 100%. So the total area under the standard normal curve is 1. Property 2 says the standard normal curve extends indefinitely in both directions, approaching but never touching the horizontal axis as it does so. Property 3 says the standard normal curve is symmetric about 0. This is an important property. That is, the part of the curve to the left of the dashed line is the mirror image of the part of the curve to the right of it. All right, so we know that normal curves and therefore standard normal curves are all symmetric. That is, 50% of the observations will lie to the left of the center point where the mean is located and 50% to its right. And property 4 says almost all the area under the standard normal curve lies between -3 and 3. Almost all the area. Why? Because by the empirical rule, 99.7% of observations lie between -3 and +3 z values. So the most important rule is the total area under the standard normal curve is 1, is the one that we are going to apply for this when finding the areas or calculating the areas from the table. But the other ones are equally important, especially property 3. We will use this property about symmetry also when in some of our calculations. All right. Here we have a section of a z-table, which we are going to use to learn how to read areas from. Right? Now, as you know, z values can be a positive value or a negative value. Most often you will have a z value which is within +3 or -3. Very rarely you will have a z value which is greater than a +3 or less than a -3. Okay, so z values can be positive and negative. So when you're given a z table, it will come in two parts. One section of the table will have positive z values, and another section of the table, which is not shown here, will have all the negative z values listed, and the z values are commonly listed on the extreme margin. So the extreme left column would be a z value, or it could be on the extreme right hand side also, and these column values are up to 1 decimal place. All right. Across on the top row next to z, we have the second decimal places for z. All right, these are the six. So if you have a z value of 1.27, all right, 1.27, okay, then you would have to go to where 1.2 is on this column in the margin, and then you also have to go across to 0.07, which represents the second decimal place in z, and then look up the value. These values in the center of the table, all right, in the body of the table, not along the margins, but inside the table, represent the areas. And the z table always gives area to the left. All right, area to the left. This is very important. You please keep that in mind. The z table will only show area to the left of a certain z value. So if this is a standard normal curve, the center point will have a z value of 0. So if we want to find the area to the left of a certain z value, let's say that is 1.34, and we extend this and we want this area to the left. All right, we want to know what percentage of values lie to the left of a z-score of 1.34. In that case, we come to this table. All right, we come to this table, and this table will always give area to the left. So we will find our 1.3. It's situated right here. All right, just below this 1.2. So locate this point first, and then, or this row first, and then go all the way to where 4 is. 4 is here, right? So the area to the left of 1.34 is 0.9082. That means all this area is 0.9082, which when converted to percentage amounts to 90.82%. All right. So this is how we look up value areas from a table. All right. So over here we have 1.23 in red, right? So the area to the left of a z value of 1.23 would be 0.8907. Okay, so let me just draw that in a curve. So we have 0 at the center and 1.23. Let's say we are looking for 1.23. Okay, this red, the values marked in red. 1.27 would be somewhere to the right. It's greater than 0, so somewhere to the right of 0. We extend a line to the curve and shade the region to the left. The corresponding area to the left is this value here, 0.8907, or 89.07% of observations lie to the left of 1.23. This is 1.23. Now, how about if they ask us to find the area to the right? If the question is, what percentage of observations are greater than 1.23, a z value of 1.23? In that case, we will need to find the area to the right. Okay, our region of interest will be this area to the right. Anything greater will occur to the right, will appear to the right. Therefore, this is the area that we want to find. How do we find the area to the right when our table only gives area to the left? For that, we have to use that special property that the total area, right? Remember the property 1 of standard normal curve said total area under a curve is 1. Curve is 1. So if the total area under the curve is 1 and the left hand side of 1.23 is 0.8907, in order to find the area to the right is 1 minus, it's going to be 1 minus, so let me write that down, area to right is 1 minus 0.8907, whatever that value is. All right, so that is how we find area to the right of a particular z value. We first have to find the area to the left from the table, and if our region of interest, if the area we are looking for is on the right hand side, you have to subtract whatever area you found from the table from 1. Okay, now later we will learn how to find area between two z values. Again, keep in mind, in order to use a table, you have to come to the table with z values and not actual values of data. All right, your actual values, observation values, should be first converted to z-values, and only then you can come to this table and refer to it for the area. Okay. Now, typically, as I said before, you will be given two sets of z tables, one for the positive z values, and then there'll be another one, which we'll see in the next slide, for negative z values. So the first, up to the first decimal place, will be located on the extreme left margin, could also be on the extreme right margin, and on the top row will be the second place decimal values for z, and then you have to look into the body of the table to find the area corresponding to a particular z value. All right. Now in the next slide uh, we will see how the negative z values look. So depending on whether your z value is a positive value or a negative value, you have to look at that part of the table. This is the table for negative z values. So on the left hand side, you will see all negative values listed for z, whereas in the previous one we had all positive values. So if you were to find the area corresponding to negative 1.2 1.20, right, then you will first refer to this particular table, find your negative 1.2 somewhere, okay, somewhere here, negative 1.2, and then go across to the second decimal point and pick up your values there. All right, now I will do a separate video with the table that you will be using for tests and go over that briefly to familiarize you with it. So here is a set of three pictures, all right, showing the shaded area for a standard normal curve. Again, keep in mind that the table, the z table, will always give areas to the left by convention. That's how z tables were created. They will only represent areas to the left of a certain z-score. So when we have to work on a problem which asks us to find the percentage of observations below or under a certain value, the first thing that you must do is to convert that value to a z value, and then you have to decide which area you are looking for. All right, if they say what percentage of observations are less than a certain value, then you will have to, it will be the area to the left of that particular z value, less than left, right? If they are asking you for observations or the percentage of observations above a certain value, then it'll be to the right. Your region of interest or the area you're looking for would be to the right of a particular value. And if they say between two specified values, then first, of course, you will have to convert those two values of observation into z-scores, and then you will find the area between the two z-scores. And to find, so let's look at the what they have stated here at the bottom. So shaded area, if it's to the left, it's very easy. Just go to the table and find the corresponding area for the particular z-score, and you got the area to the left, because if it's less than, its area to the left, and your table will directly give you the area to the left. If it's area to the right, then of course you still have to go to the table with your z-score value, but that will give you the area to the left. But you're not interested in the area to the left, you're interested in area to the right. So you have to use that property that the total area under the curve is equal to 1. So you have to do 1 minus area to the left of z. will give you the area to the right. So this area would be 1 minus area to left. The table will always give you area to the left. Do not forget that. And then between two values, all right, you have to first find the area to the left of the higher z value. All right, let me write that down here. So steps are find area to left. And how you're finding the area from your table? Find area to left of higher z value. And then find area to left of lower z value, and then subtract. All right, area to left, and then we subtract. So let me just explain that. What we will be doing is we will first be finding area to the left of z sub 2, all this area, correct? That would be area to the left of z sub 2, but we are not interested in this part of the area of this part of the curve, because we only want the area between z sub 1 and z sub 2. So this part of the area is the area to the left of z sub 1, isn't it? So we have to subtract this area to the left of z sub 1 from all this area, okay, which will give us only this area at the between the two z values. All this has to be subtracted. Okay, so we have to remember these rules when finding the area. We have to first decide which area we are looking for and then take the appropriate steps. Now we kind of already went over this previously. If you think that you've understood, then how to find z values, or rather how to find areas for particular z values to the left or right or in between, then you can just skip through these. But if you think another review would help, then let me just go through it here. Finding the area to the left of a z-score. The z-table, keep in mind, always gives area to the left of the z-score. All right, so and always you have to come to the table with a z value and not actual values. The z value over here given to us is 1.23. It says find the area to the left of the z-score, z value being 1.23. So we have to first go down the extreme left hand side column, look for 1.2, because this column only gives area to one decimal place, and then there's a 3 here. For that we have to go across 1.23 and then pick the value at the point of intersection. So over here we go, sorry, let me just switch to my pencil here. So go all the way across and then 0.03 would be this column. So pick the value at the point of intersection. So 0.890, and that's area to the left. The table only gives area to the left, and you are looking for area to the left, right? This side of the area, and that's 0.8907, which translates to 89.07%. Okay, now it's always good practice to draw your curve with z values, all right, the broad z values showing with 0 in the middle, in the center, then 1, positive 1, 2, 3 to the right, negative 1, negative 2, negative 3 to the left, and show the region of interest, show where 1.23 is, or whatever z value you're looking for is located on the curve. Extend the a vertical line up to the curve to touch the curve, and then shade your area of interest. All right, that's the best practice, and that will help you find what you are looking for easily. All right. To find area to the right of the same z value 1.23, you first have to find the area to the left, and then from 1 you will be subtracting whatever area you found for the left. So again, draw your curve, show where z equals 1.23 would be located on this curve, and then shade your region of interest. Here they said clearly that just a second, here they stated clearly to find the area to the right. So your area would be this area to the right of wherever z equals 1.23 is located. All right, and then first you will find the area to the left, which is all this area, that's 0.0.8907, and then to find the corresponding area to the right, it's 1 minus 0.8907. Okay, which is 0.1093. So 10.93% is the area to the right of, well, the area is 0.1093. However, in percentage, it's 10.93% is the percentage of observations to the right of z equals 1.23. Here we've been asked to find the area between two z values. So it says find the area between z equals 1.0 and z equals 2.0. So again, draw your curve and then show where 1 and 2 are on the curve. These are positive values, so they would appear to the right of the center point, 1 first and then 2 further right. Extend the lines up, all right, the vertical line up to meet the curve, and the same for line also from 2. Do the same thing for pull up a line up to the curve for 2, and then shade the region between 1 and 2 to indicate the region of interest. All right, this is our region of interest. Also, it's because we will use this term when solving problems on this chapter. Region of interest, which is the area we are looking for. So this is not area to the right, nor is it area to the left. It is the area between two z values 1 and 2. Okay, and for that we first find the area to the left for the larger z value, for the higher z value, in this case 2. So we are essentially finding first finding all this area, all right, from 2 everything to the left, this area, and then find area to the left for z equals 1, which is the lower value. All right, so that would be all this area. Oops, let's use another color. Hopefully this one. All right, all this area. So that needs to be subtracted from the higher value because we only need this area. All right, the area between 1 and 2. We do not need the area to the left of 1. All right, we just need the area between 1 and 2. So subtract the area of the smaller z value from the area of the higher z value. So now if I look up the values on this table here, just a second, on this table here, first look up the larger value, which is 2. So that would be 0 point. All right, find area to left of z equals 2, and that value is 0.9772, and then find area to left of 1, z equal to 1, and that value is 0.8413. All right, so 9772, and then subtract the two values. All right, subtract the two values. Okay, so this is going to be the way we go about finding different areas to the left, to the right, or in between two z values. But we will work through a worksheet with all these exercises put together, and I will put up video solutions for that too, and that will give you another revision of this topic. Now, so far we were given z values and we had to find areas to its left, to its right, or in between two z values, right? So we started off with a z value and we came up with the corresponding area. The converse situation is when they give you the area to the left or to the right, and you have to come up with a z value. Right? We will be given an area, and then we will the ask will be to find the appropriate z value whose area to the right is something, area to the left is something, could be anything, whatever the value of the area that they give to us. We have to find the corresponding z value. Now, before we go into that, we have to first talk about the notation, a specific notation called z of alpha notation. Area is denoted by the symbol alpha, the Greek letter alpha. All right, and we write z of alpha. All right, z, and then alpha will be a specific area. So z subscript alpha tells us a z value. The way we read it should be z, a z value. Let me just write it more explicitly. Z value whose area to the right, and be very careful here, to the right, not left, to the right is alpha. That is how this specific notation has to be interpreted. We are looking for a z value whose area to the right is alpha. So whenever you see this notation, keep in mind that the alpha value they are talking about is to the right of a certain z value, right? Now, the table, however, will always give us area to the left. But whenever you see this notation, and that's specific to this notation, that's how I guess statisticians decided to interpret the notation. They kind of standardized it, that whenever we have this notation, it will mean that alpha, that particular area value, lies to the right of that z value, right? So make sure there's no confusion about that. The table, however, will always give you area to the left. All right, so let's go a little further into situations where we will be given the area or the alpha value, area denoted by the letter alpha. We'll be given the alpha value. How do we find the corresponding z value? And as we will see, we will be doing just the opposite of what we did when finding z values from alpha. When finding alpha from z values, we will kind of backtrack the steps. So how do we go about finding the z-score for a given area? The question here says find z of 0.025. So this, as you can see, is in the z of alpha notation, because 0.025 is a subscript of alpha. Therefore, we should read it or interpret it as find the z-value whose area to the right is 0.025. All right, so that's how we should be interpreting this notation. When they say find z of 0.025, 0 sub 0.025, that means they are asking us to find find the z value whose area to the right, and let me underline that, is 0.025. So here they've drawn a picture. We don't know what the z value is. We have to find that z value whose area to the right is 0.025. Of course, we have to consult the table to find the z value. What we do is, we remember the table will only give us values to the left. So in this case, we will first have to find the area to the left of 0.025 by subtracting 0.025 from 1. So the first step was to subtract alpha from 1 to get area to the left, All right, and then we have to go to our table and search in the body of the table for 0.975, which is area to the left. All right, and then we will find the corresponding z value, and we will that will be the z value whose area to the right is 0.025 and whose area to the left is 0.975. All right, so that's how we'll go about it. I'll try to find a slide where we where we do or find the z value from the table. In the second example, z of 0.05, that means find the z value whose area to the right is 0.05. That's what this notation tells us. So again, they've drawn a picture here. Again, this is a standard normal curve. The z values represented along the horizontal line, the horizontal axis. We don't know where the z value is or what exactly the z value is, but just mark it at a certain point and show the area to the right as 0.05. Why? Because of this particular notation, that z of alpha notation they have used, right? And then because this is area to the right and our table only gives area to the left, we have to find the area to the left of this cutoff point, this mark here, by subtracting 0.05 from 1. So this area essentially is 1 minus 0.05. So you're going to take this area 0.95. They've shown the work here. They've taken this area to the table and searched in the body of the table for 0.95, and then they came up with the corresponding z value for it. So let me see if the next slide is a table which I can use to come up with, or to show, to demonstrate how we can look up the area to find the z value. Now here's an example on how to look up the z value from a given area. So let's say we were asked to find let's say we were asked to find z of 0.96. So z of alpha notation here. So that means the area to the right of a certain z value is 0.96. So if let's say that particular z value would be over here, 0.96 is a big area, right? Almost close to 1. So that means, and so it'll be a z particular z value will be pretty much to the left end of the curve. So if we mark this area as 0.96, we want to know the corresponding z value. We will definitely first subtract 0.961 minus 0.96 will give us a value of 0.04, which is the area to the left, correct? So we have our area to the left over here, area equals 0.04. Now we can go to our table, all right? And what we have to do is we have to search for 0.04 inside the body of the table, all right? It's a hard hunt because all these numbers are swimming before us, and it's really an eye test. So we'll just have to look it up on the table, stay focused for 0.04. So once we locate 0.04, which we see over here, the closest value, this is to the 4 decimal places, is 0.0401. Correct? So 0.04, this is the value we will first pick up, and then we will have to look for the corresponding z value. So we go all the way to the left first, all right, across the row. So pick up the z value, which is negative 1.7, right? It's negative 1.7 to 1 decimal place, and then up here from this point, go up the column to pick up the second decimal place, which is 0.05. So negative 1.75 is your z value. So first we look for the area 0.04 inside the table, inside the body of the table. Again, it's going to be a little bit difficult because uh, we have so many numbers, and we are locating that particular specific number from this whole group of numbers. But that's how it works inside the table. Then find the value. Once you find the value from that particular value, go across horizontally to the z value, and then go up to the all the way up to the top row to pick up the second decimal of the z value and put them together. The z score is negative 1.75. So the z value here is negative 1.75. All right, negative 1.75. So that's how we go about finding a z score from a given area using a table, right? Let's go over the steps of finding a percentage or probability for a normally distributed variable. Now, keep in mind that the area under the curve represents proportions. It represents uh, relative frequencies, proportions, relative frequencies, same thing. And then it also represents probability, because the formula for relative frequency and probability are the same, F over N. So depending on what we are working with, we can interchangeably use the terms probability as well as proportions for areas under the curve. And once we have the area, it's going to be a value between 0 to 1. The total area under the curve is 1. Once we have the specific area, we can convert it to percentage by multiplying by 100. And here are the steps. We've already gone over that, but let's now formally look at all the steps put together. So step 1 is sketch the normal curve associated with the variable. Like I always say, draw a picture. We first draw the standard normal curve. Doesn't take much time. All right, a horizontal line. Okay, just a horizontal line, and above it a bell-shaped curve, and then show the center point as 0, positive 1, 2, 3, 2, 3 to the right, positive, negative 1, negative 2, and negative 3 to its left. All right. So we sketch the curve and then shade the region of interest and mark its delimiting x values. So if we are given x values, that means actual observations, then we will first have to show those values. Instead of a standard normal curve, we will have to show those values on the horizontal line. And then we have to, most definitely, we have to convert those x values, the x values you're working with, into z-scores, and maybe redraw the curve, this time with z values. All right, so find the z-scores for the delimiting x values, and the formula for the z value is x minus mu over sigma, correct? And then we will use the z table to find the area under the standard normal curve delimited by z-scores. All right, the way we learned how to find area, if they ask us to find area between two values, we have to find the area of the larger minus area of the lower, all areas to the left. If it is find area to the left, then then whatever you get from the table is your area. And if they are asking for area to the right, you have to find the area from the table and subtract it from 1. Okay, and then if they are asking for percentage, you have to convert that to percentage. Here's an example to demonstrate how to find the area for a typical example. It says determining the percentage of people having IQs between 115 and 140. So the mean, this is curve, a normal curve, the mean is 100 for IQs and the standard deviation is 16. So these have also been given to us, and the two observations that we are interested in are this x sub 1 and x sub 2. All right, so these are individual observations. We have to find what percentage of people lie between these two IQ scores. All right, so again, the first step was to draw a normal curve with the mean value. These are actual values, right? So show your mean value at the center, and then 115 would be to the right of 100 and 140 would be further right of 100 and 115. So mark those areas, and then we want the percentage between two values, so we have to shade the area between these two observations. Okay, so that's step 1 and 2. In the third step, we have to find the corresponding z values. So the corresponding z value for 115. So what we essentially did to find 0.94 was take your z value, z of the formula for z, let's write the formula first, is x minus, just a second, excuse me. So x minus mu over sigma. Okay, so if we consider 115 as x sub 1, then I'll mark this x sub 1. So we will do this 115 minus 100 divided by sigma is 16. You have to use the formula for z, and that when you do this calculation, 15 over 16 will give us a z value of 0.94. And then that would be z sub 1. All right, this here. And next, z sub 2 would be, this time you're using x sub 2. So it would be x sub 2 minus mu over sigma. So 140 minus 100 divided by 16 is 40 over 16, which gives us a value of 2.50 for z sub 2. So to find this area, what do? We first find area to the left of, all right, find area left of 2.50, whatever that may be, and then find area. So we first find all this area. We find all this area, which is to the left of 2.50, and then find area to the left of 0.94. That means everything to the left of 0.94 would be, let's take another color here and shade it, all this area, right? All this area needs to be found to the left of 0.94, and then at the end we subtract, okay, subtract the two values, okay, the lower from the higher. All right, we do the subtraction, and that will give us this area between 115 and 140, which we can convert to percentage. Okay. All right. So this is the way we would go about step by step to find areas or percentage values between two observations, or to the left, less than a certain observation or greater than a certain observation. We will now list the steps of determining observations from percentages or probabilities. In other words, we will be given the area or the probability values. In that case, we will be given the alpha values, or we could be given the percentage values. Remember that percentages are just a conversion of the area, correct? A transformation of the area by multiplying the area by 100. So they represent pretty much the same thing. So given an alpha value, what are the steps we must follow in order to first find the corresponding z value, and then from the z value, how do we find the actual observed values? So to determine the observations corresponding to a specified percentage or probability for a normally distributed variable, step 1 is sketch the normal curve associated with the variable. Always start by drawing the curve, right? And then once you have your curve, shade the region of interest. So here we are sketching the normal curve, and then we shade the region of interest. That means the area that has been given to us. We have to show that on the curve. And then step 3, use the table to determine the z-scores, delimiting the region found in step 2. And finally, in step 4, we find the x value having the z-score found in step 3. So in other words, what we do is in step 1, we just draw our curve, our normal curve, and of course we will be given an alpha value. So if they say z of let's say if they want us to find the z value whose area to the right is 0.25, right, alpha value whose area which is 0.25, that means when you sketch your normal curve, you have to show your alpha value. All right, it'll be to the right. That's what the notation says. So this region is 0.25, and the corresponding z value will be located at this point, at a particular point from where that area starts, right? And so shade the region of interest. Here we have shaded the region of interest. Okay, and then we have to go to our table with the alpha value and find the corresponding z value. And then once we know our z value, we can find the observed value from the formula z equals x minus mu over sigma. We can solve for x. If we know our z value, we know our mean, we know our standard deviation value, we can always solve for x and find its value. But the formula for x after you solve for x should appear like this. X should be equal to mu plus z times sigma, right? Now, the last topic in this chapter is about assessing normality using normal probability plots. What this means is that if we want to decide from the data set whether it's normally distributed or not, then one way of coming to that conclusion is by using what's called normal probability plots. So here are the steps. It says guidelines for assessing normality using a normal probability plot. To assess the normality of a variable using sample data, construct a normal probability plot. So there's a way of creating the probability plot, which I will talk a little more in the next slide. And then by looking at the plot, if the plot is roughly linear, you can assume that the variable is approximately normally distributed. And if the plot is not roughly linear, you can assume that the variable is not approximately normally distributed. And these guidelines should be interpreted loosely for small samples, but usually interpreted strictly for large samples. All right, so let's look into an example in the next slide of this. Here's an example demonstrating the normal probability curve. We have data given here, which is adjusted gross income in dollar thousands. So these are actual data sets. The first step is to arrange the data from lowest to the highest value in increasing order or ascending order, right? So here the data is arranged 7.8 first, and then the values increase all the way to 93.1. Now on the second column here is the column for the normal score. So each data value has an associated normal score, and these values are obtained from a table. All right, so a table or a graphing calculator with a statistical package also can calculate the normal score for you for each of these values, and these normal scores are really based on the position, and that's the reason we arrange them in increasing order. So position 1 is 7.8, its normal score is negative 1.64. For 9.7, it's negative 1.11, and it depends also on the size of your data, right? So here I guess we have 1, 2, 3, 4, 12, right? 12 data points. So uh, based on the number, the sample size, as well as the position of the data values, we find the normal score. Normal score is nothing but the z-score really. And then we plot all these normal score values. Along the horizontal line, we have the adjusted gross income. We scale the axis in intervals of 10, starting from 10. And along the y-axis, we have the normal score values. Remember, z-score values extend from -3 to +3, correct? So that's how we scale the y-axis and show the normal scores. And then we plot each normal score value based on its adjusted gross income over here as a graph. And these are just plots. You do not need to really connect the dots, but at the end we observe for a linear pattern in these dots, all right, in these plots. If it follows a linear pattern, then we can conclude that it's normal distribution, all right. If it does not follow a linear pattern, in that case, it's not normally distributed. So this brings us to the end of the chapter on normal curves. We will, however, do some worksheets. I will go through the problems in the worksheet on this chapter and talk more about the process, show you the step-by-step process on the various problems in there, how to find z values, how to find observations with alpha values or the area probability values given, or how to find alpha values given a z value. So we will go through those exercise for some extra practice and to apply whatever we have learned in this lecture.